Welcome back. So we are in module 5, lecture 5, and we are discussing about the coagulation, precipitation and heavy metal removal. So the concepts covered in this topic will be on chemical precipitation for removal of heavy metals. We will talk about the solubility product. We will talk about the steps in the precipitation method. Then we'll talk about the removal of various heavy metals by chemical precipitation method, the limitations of the chemical precipitation methods for the removal of heavy metals, and then we will do some numericals based on the solubility product. So the heavy metals in wastewater, we know that there can be metals present in the water or wastewater. So the metals or the heavy metals are defined as the metals with high density, atomic weight or atomic numbers. So when the density of these metals is greater than 5 grams per cubic centimeter, or they are having a relative atomic mass which ranges from 63.5 to 200.6, so they may be classified as heavy metals. So these heavy metals may be essential nutrients, for example, iron, cobalt or zinc. So they may be necessary for the body, and that's why they are essential nutrients. And similarly, they can be harmless also. For example, the ruthenium, silver, indium, so they can be termed as harmless. And there can be heavy metals which are of a major concern. For example, the metals like arsenic, cadmium, mercury, lead, chromium. So they can be highly toxic, they can be highly poisonous, as well as they can be highly carcinogenic in nature. So there can be natural factors which may induce these heavy metals into the environment. For example, it can be by the weathering or the soil erosion, it can be the surface runoffs, it can be the volcanic eruptions that can induce these metals into the environment. The anthropogenic reasons for the induction of these heavy metals into the environment is generally the industrial effluents, for example, the industries like metal smelting, electroplating processes, the leather tanning, textile, mineral extraction, and nuclear power. So they can induce these metals into the environment. So the municipal effluents may also contribute to the heavy metals. For example, it has been reported that municipal effluents may contain lead, chromium, mercury, and arsenic. So the major concern is that these heavy metals can be quite toxic and they can bioaccumulate. They are non-biodegradable in nature, so that's why they generally bioaccumulate inside the body as they are not metabolized and they remain into the body, and slowly they may accumulate inside the body, and then once the threshold level is exceeded, and then they start showing their effects. So these metals can be the threat to human life as well as to the environment, and because of their bioaccumulation tendencies, so they can also biomagnify in the food chain, and that may cause problem to the secondary consumers who are upper in the food chain. So the irrigation with wastewater which contains heavy metals, so it can also result in the contamination of the soil, it can result in the contamination of groundwater, as well as these metals can also accumulate inside the vegetation, and this may also form a part of the food chain. So that's why it is very important that the wastewater treatment must take into account the removal of the heavy metals so that the environment can be protected as well as the human health can be protected from these metals. So there can be metals like arsenic, barium, cadmium, copper, mercury, nickel, selenium, zinc, chromium, lead. So these metals must be removed from the water or the wastewater so that these may not come into the food chain, and this may ultimately not come to us. And there can be a number of methods which can be employed for removal of these heavy metals from the wastewater. For example, we can take help of the chemical precipitation, which we will be discussing at length during this lecture. We can also go for the carbon adsorption, we can go for ion exchange processes, we can also go for the membrane processes like reverse osmosis. So for the treatment of the wastewater, the most common methods that is employed is the chemical precipitation. However, the choice of the method will depend upon the factors like the type and the concentration of the heavy metals which are present in the wastewater. The characteristics of the wastewater will also decide about the choice of the method. And similarly, the environmental regulations, the effluent standards, that is the level up to which these metals needs to be treated. So that also decides the choice of the method. So commonly when we go for the chemical precipitation, so we can precipitate these metals in form of hydroxide, sulfides or sometimes carbonates also. So here, when we go for the precipitation method, so solubility equilibrium plays a very important role during the precipitation of certain ions. Or basically, when we are talking about the heavy metals here, so the precipitation of the metals will be influenced by the solubility equilibrium of these compounds. For example, if we consider a slightly soluble compound CaAb, let's take it as C is the cation and A is the anion which is present in this compound. So it may dissociate into the anions and the cations as given in equation 1. So here you can write down the equilibrium constant for this equation. So this will be the K equilibrium is equal to C raised to power A and A raised to power B as given by the equation. And here we have not taken any denominator because denominator represents the solid form, that is here CaAb, it represents the solid or the precipitated form, and solid is pure and basically it represents the unit activity. So that's why it is taken to be 1, and that's why the equilibrium constant here is taken to be C raised to power A and A raised to power B in this case. And this equilibrium constant can also be referred as the solubility product constant, and we generally use a term that is KSP for the solubility product constant. So this solubility product constant can help us in determining that whether the precipitation will happen or not. For example, if suppose the ionic product of C and A here is less than the KSP values, right, at the given temperature, so we can say that the solution is undersaturated and we need to add more ions here so that the saturation will happen and then the precipitation of these ions basically of the compound that is formed by this reaction of these ions, so that can happen. Similarly, if the value of the ion product here C raised to power A and A raised to power B is greater than the KSP values, that is the solubility product constant, so we say that the solution is oversaturated and the precipitation will happen. And if this ionic product is equal to the KSP value, so this means that at that point the precipitation has just started to happen. So the KSP value is higher always for the freshly formed precipitate in comparison to the old precipitates. And this phenomena is also known as the aging phenomena. And this happens because the freshly precipitates may be more soluble in comparison to the old precipitates, as the old precipitates are having the crystals which are ordered, which are inactive, which are less soluble and larger in size. That's why the old precipitates are having the lower KSP values in comparison to the freshly formed precipitates. Similarly, we can have a common ion effect also which will affect the solubility equilibrium. For example, according to Le-Chatelier's principle, if either C or A is added to the system, so if we see the equation 1 here, so this basically if we are adding C or A to the system, so this equilibrium will shift towards the left side. So this means that it is shifting more towards the precipitation side. So this means that the solubility of the precipitates then decreases. And this effect is known as the common ion effect. For example, we may have seen that if we are using the sea water which contains high amount of sodium and if we try to use soap with it, so soap does not lather because of the common ion effect, and this basically may be taken as the hardness in the water, and that is also referred to as the pseudo hardness because it is due to the high sodium ion concentration which is there in the sea water, which basically does not allow the sodium salt which is present in the soap to basically lather. So this effect is called the common ion effect. Similarly, if we are adding ions which are other than the ions present in the precipitate or which are also known as the indifferent electrolytes, so this will reduce the activity of the C cations as well as the anions, because the ionic strength will increase. As the ionic strength increases, the activity of the cations and anions present in the solution, so they will decrease. And let's say now the K equilibrium will be equal to gamma m, where gamma m is the activity of cations and gamma m also represents the activity of the anions. So the new value of the K equilibrium, that is K equilibrium dash, so this will be equal to K equilibrium divided by the gamma m whole square, where gamma m is always less than 1 because the activity in a high ionic strength is less than the actual concentration that has been added to the system. So this will increase the solubility of the precipitate, and on addition of the indifferent electrolyte, you will always find that the solubility of the precipitate will increase. So these are the value of the PKSP. PKSP here refers to the minus log of KSP. So these values are given for various type of metal hydroxides as well as sulfides. So for example, you can see here that the cadmium hydroxide and cadmium sulfide, so the values of PKSP is 13.93 and 28 and so on for the different type of metals precipitates, for example, chromium hydroxide, copper hydroxide, copper sulfide, iron hydroxides and sulfides, lead hydroxide and sulfides, mercury hydroxide and sulfide. So they all are given in this table, and we can refer this table so that we can find out that what would be the solubility product for such type of precipitations, and then we can calculate that how much precipitate will form, or basically how much ions needs to be added so that the precipitation of these metals can occur. The heavy metal removal technologies includes the conventional precipitation that we are just discussing. So we can precipitate the metals in form of hydroxides, we can precipitate the metals in form of sulfides, we can precipitate the metals in form of carbonates. We can also go for co-precipitation where the metals may be precipitated along with the precipitate of different compounds. So these metals can also be entangled or adsorbed onto the precipitate, which is otherwise not for of the metals which are there, right? So this leads to the co-precipitation of these metals. Similarly, when we are having industrial wastewater, so in that case, it is possible that the metals may be present in complex form or they may be chelated industrial wastewater. So these chelated or complex metals can be removed by using advanced precipitation method where we use dimethyl thiocarbamate, where we use diethyl thiocarbamate, or we can use trimercaptoastriazine or trisodium salt for the precipitation of such complex metals in the wastewater. The other methods which can be used for the removal of the heavy metals may be adsorption. For example, we can use here activated carbon. So the adsorption we have already studied, and we know that how we can use different type of adsorbents like activated carbon, or we can also use new type of materials, cheap materials also for the adsorption of the metals by using certain adsorbents like biochar, etc. So this method can be used for transferring the metals from the water to the solid form. Similarly, ion exchange process also we have discussed, and we can replace the metals which are present in the water or wastewater by sodium or H plus ions, which basically goes into the water, and we can also recover the metals from this ion exchange process. We can also use the membrane filtration for the removal of the heavy metals like reverse osmosis, nanofiltration, ultrafiltration, so that the metals can be removed from the wastewater. Biological methods have also been used, for example, the bioremediation by using different species of bacteria, algae, and fungi. So they also can be used for the removal of the heavy metals from water or the wastewater. Similarly, we can also use a method which is called electrochemical methods, and here we can go for either electrocoagulation of the metals, or we can deposit these metals onto the cathode by passing the electrical current through the wastewater. So these methods can also be used, but we have already discussed that the method which is commonly used, because we are having a very large volume of the wastewater which we have to handle. So the efficient method for by which we can remove the metals from the wastewater can be the chemical precipitation. And if we want to recover the metals, so we can go for the methods like ion exchange, we can use membrane methods, or we can also go for the electrochemical methods for the recovery of the metals from the wastewater. So then the selection of the appropriate method, it depends upon the characteristics of the wastewater and the desired treatment goals. Or basically we can say that which method will be best for certain characteristics of the wastewater, so that we have to find out, and then we also have to look at what are the desired treatment goals, how much reduction of the metals or how much removal of the metal needs to be done, so that appropriate method can be chosen from whatever the methods we have discussed till now. And similarly, we have to also see that if whatever the methods we are using, so it has no adverse environmental impact, and it should also basically comply with the regulatory standards. So when we go for the precipitation methods, so the steps that we follow are generally adding of the chemicals to the wastewater so that precipitate with the heavy metal ions it can form. Then we can go for the sedimentation or filtration process so that we can separate out the sludge from the wastewater. And here we can use the salts, like for example, we can use lime here, calcium hydroxide, we can use sodium hydroxide, and we can also use other metal salts when we want to remove it in form of carbonates or in form of sulfides. So we have to first of all identify the heavy metal, that what type of heavy metal is present in the wastewater, what is the concentration of the heavy metal that is present, and then we have to look for the appropriate precipitation agent that can be used for the optimum precipitation of such heavy metal. We know that the optimum pH is required so that the metals can be precipitated out from the wastewater. So this means that we have to optimize the precipitation process and we have to adjust the pH of the wastewater so that the metal hydroxides or the metal sulfides or the metal carbonates, they are least soluble at that pH and they can be removed easily from the system. And generally for many heavy metals, this pH range is generally alkaline. So then we have to add the precipitating agents, where we can add one precipitating agents, or we can use a combination of the precipitating agents, where we can use either lime, we can use sodium hydroxide, or we can use the metal salts. So once these precipitants are added, so they will form insoluble metal hydroxide precipitates, and these metal hydroxide precipitates can be separated from the wastewater. However, we have to ensure that a thorough mixing should be done as soon as we add the chemicals, so that the proper contact is established between the precipitating agent as well as the heavy metal ions. As we have already discussed, that the rapid mix is very much required for the coagulation and flocculation process. And similarly, we can also add some flocculants so that the precipitate that is formed, so that we form a larger flocks. After this, we may pass it to a sedimentation tank where these precipitates may be settled out, or we can pass it through a filtration system where the precipitates can be separated out from the wastewater. After this, we may also take it to other treatment steps also if it is required. For example, if we are having presence of other contaminants in the wastewater, so we may take it for adsorption process, or we may take it for the filtration, or we may take it for other processes like oxidation, etc., so that the water is treated for the requisite contaminants which are present in the wastewater, and then we can polish the water in that way. And the last step is that we also have to monitor and control the processes. For example, a continuous monitoring is required. Like, for example, we have to always monitor what is the pH, what is the metal concentrations which are coming out in the effluent. We have to also see that what is the effectiveness of the precipitation that we are doing, so that we can maintain the optimum treatment conditions. So the stoichiometric ratio of the reactions, so it needs to be studied so that we can calculate that how much precipitation agent is required for the optimum precipitation of certain metals, and so this will also help us in minimizing the addition of the excess chemicals in such a way. So we can see here that this graph shows that how the concentration of the various metal hydroxide, it varies with the pH. So we can see here that a number of metals, like for example cadmium hydroxide is there, which is having minimum solubility at a pH of nearly 12, and similarly we can also see here that the copper hydroxide is having a minimum solubility of nearly 9 or so, right? And so this means that for a different type of metal hydroxides, we are having some optimum values of the pH at which the solubility of those hydroxide is minimum. As these metals may be amphoteric in nature, so at the low pH as well as at the high pH, they may be in the soluble form, and there can be an optimum pH values at which these metals may precipitate as hydroxide, and the solubility may be minimum at a certain pH values. And these curves that we are seeing here, so this is based on the mononuclear species, right? And if we want to find out that what can be the range for the wastewater treatment, we have to perform the actual test or pilot scale test, so that we can find out that what can be the optimum value for a certain type of wastewater. So similarly, we can see here that precipitation of sulfides with the pH, right, is given here, and we can find out that for the mononuclear species, if only those species are present in the water, so what can be the optimum pH at which these metal sulfides can precipitate. Right? So it will also depend upon the characteristics of the wastewater, that it will also depend upon the concentration of organic matter, it will depend upon the temperature, optimum pH values. So that's why it is very important that we go for the bench scale or pilot scale test before we find out the optimum pH for the precipitation of a certain metal. So now we'll discuss about the different type of metals which can be present. For example, we'll talk about the arsenic, and the arsenic may be used in the metallurgical, in the glassware, in the ceramics, in the tanneries, in the dye making, pesticides, and petroleum refining. So this arsenic, if it is taken by the humans in high amount, so it may lead to the nervous system disorder, it can lead to the liver cancer, it can lead to kidney and bladder cancers, it can lead to skin cancer, it can lead to diabetes, lung cancer, as well as the cardiovascular diseases. So for the drinking water standards, it is required as per IS 10500 that the total arsenic should not exceed 0.01 milligram per liter in the drinking water, whereas the effluent discharge into the inland surface waters, the arsenic should not be greater than 0.2 milligrams per liter. So we can remove the arsenic by precipitation, and when we want to remove the arsenic by precipitation, we should ensure that the arsenite, that is arsenic 3, should be converted into arsenate, that is arsenic 5, because it precipitates better than the arsenite. So this means that we have to oxidize the arsenic 3 to arsenic 5 before we go for the precipitation method, and we can treat the arsenic by using hydrogen sulfide or sodium sulfide at pH 6 to 7, followed by filtration, which can lead to 0.05 milligram per liter of arsenic in the effluents. Similarly, the filtration through the activated carbon filter may also lead to 0.06 milligram per liter of arsenic in the effluent. However, the co-precipitation with ferric hydroxide have shown to be the best removal, and we may get around 0.005 milligram per liter of arsenic in the effluents. So the barium is used in different industries, for example, in paints and pigments, for glass, ceramics, dye manufacturing, vulcanizing of rubber, explosive manufacture. So here this the barium, if it is taken in high amounts, it may lead to the muscle weakness, it may cause the brain swelling, it may cause difficulty in the breathing, we may have increased BP and stomach irritation, etc. As per IS 10500, the barium should not exceed 0.7 milligrams per liter in the drinking water. So if we target barium, so the precipitation as barium sulfate is very efficient, as the barium sulfate is having very low solubility. So if we go for barium sulfate precipitation, we may get around 0.03 to 0.3 milligrams per liter in the effluents, and typically we can get a concentration of nearly 0.5 milligram per liter in the effluents. Though ion exchange and electrolytic treatment may also be used, but they can prove to be expensive. So cadmium may also find in the water or the wastewater, and this may happen because of its use in number of industries, like it can be used in nickel cadmium batteries, it can be used in solar cells, it can be used in metallurgy, alloys, ceramics, electroplating, photography, pigments, plastic stabilizers, and it also absorbs neutrons, so it can also be used in the nuclear reactor. So if we take high cadmium, so it may basically lead to a disease which is called Itai disease. So once this has happened, that during the zinc mining, it has led to the very high concentration of cadmium in the Jinzu River in Japan. So which led to the replacement of calcium by cadmium in the bones, which leads to the softening of the bones, and it also led to the kidney disease. So nowadays, it is being seen that the trend for the cadmium in the rechargeable batteries and solar cells is increasing, whereas in the pigments, coating and plating, stabilizer or alloys, it is decreasing. And in the drinking water, it should not exceed 0.003 milligrams per liter, and the effluent which is discharged to the inland surface water, so it should not exceed 2 milligrams per liter. So if we talk about the removal of the cadmium by precipitation method, so hydroxide precipitation at pH 10 to 11 may lead to 0.05 milligram per liter in the effluent. If we co-precipitate the cadmium with ferric hydroxide, so it may also lead to around 0.05 milligram per liter in the effluent, whereas sulfide precipitation is the best, which leads to around 0.008 milligrams per liter of cadmium in the effluent. So chromium may also come into the environment through various industries like chrome plating, dye manufacturing, textile industries, aircraft, leather tanning, wood preservatives, and mud drilling. So the chromium may be present in the water in major two forms. For example, it may be present in trivalent form or it may be present in the hexavalent form. So this hexavalent form is quite toxic, basically cytotoxic in nature, mutagenic, carcinogenic. It can cause chromosomal damage, and also it can cause oxidative protein changes. Whereas if we are inhaling the high amount of hexavalent chromium, so it can cause a lot of problems, like it can cause nose ulcers, irritation, anemia, It can basically cause phase erythema and a number of problems related to the lungs. So the removal of the chromium may take place, that is, we have to first of all convert chromium 6 to chromium 3, right? And then this can be precipitated as chromium hydroxide. The chromium in the drinking water should be very, very low, that is, it should be nearly 0.05 milligram per liter in the drinking water. And when we are discharging the effluents to the inland surface water, so it should not exceed 2 milligram per liter as total chromium, whereas the chromium 6 plus, it should not exceed 0.1 milligram per liter. So when we want to reduce the chromium 6 to chromium 3, so in that case, we have to use iron salts, for example, ferrous salts we can use, sulfur dioxide we can use, and sodium thiosulfate we can use, so that we can reduce chromium 6 to chromium 3, and in turn the ferrous is oxidized to ferric and the sulfur dioxide is oxidized to sulfate, and this happens in a acidic medium. After that, we have to add lime so that the chromium hydroxide can be precipitated out. So if we want to remove 1 ppm of chromium, so we may require around 2.81 ppm of sodium thiosulfate, which is 97.5% pure, 1.52 ppm of sulfuric acid, 2.38 ppm of lime, and 1.85 ppm of sulfur dioxide. And we have to always use excess of sulfur dioxide so that we can counteract the dissolved oxygen which is present in the water. For example, here we have to add 35 milligram per liter of sulfur dioxide additionally. So we can go for the removal of the chromium in the batch system also, as well as in the continuous system also. So when we are having very, very small plants which are having discharge less than 114 cubic meter per day, so in that case we may go for the batch system where we add the chemicals simultaneously in a batch reactor, and then we may treat the water or the wastewater in batches. Whereas if we want to treat it continuously, so then we have to have different reactors. For example, the first reactor that we are seeing here, in this reactor the chemicals may be added, like sulfur dioxide may be added from here. We can add the ferrous salt, we can add sodium thiosulfate, and we can also add here acid, so that the chromium 6 is reduced to chromium 3 in this reactor. Right? And then we take this effluent to another reactor where we increase the pH, where we add lime to it, so that the pH may be increased and the chromium, which has been converted to chromium 3 now, it can be converted to chromium hydroxide precipitate. And then we can take it to a settling tank where basically this sludge may be settled out and the effluent may go to the disposal. And this is used for the large plants where basically we are having the flow greater than 114 cubic meter per day. So the copper is also used in number of industries. For example, it is used for the metal process, it is used for pickling baths and plating baths, chemical manufacturing units, etc. And high doses of copper may lead to the liver damage, abdominal pains, cramps, nausea, diarrhea, and vomiting. And it can also cause Wilson disease, where basically the copper may get accumulated into the brain or the liver. So we can use different methods here for the removal of the copper, for example, precipitation, ion exchange, evaporation, or electrolysis. So they can be used for the removal of copper. And as per the drinking water standards, the copper in the drinking water should not exceed 0.05 milligram per liter, and as well as in the effluent discharge, it should not exceed 3 milligrams per liter. So if we want to remove the copper by using precipitation method, so we have to have alkaline pH where the copper may be converted to copper hydroxide, and it may result in 0.02 to 0.07 milligram per liter in the effluent. But if the sulfate is present and we are using lime, so in that case the calcium sulfate may be precipitated out, and which may interfere with the recovery of the copper from the copper hydroxide sludge. Similarly, we can also use oxidize the copper to copper oxide, which is having a minimum solubility between pH 9 to 10.3, and it can also result in 0.01 milligram per liter of copper in the effluent. Copper can also be precipitated as copper sulfide at pH 8.5, and it may result in 0.01 to 0.02 milligram per liter of copper in the effluent. So iron can also come into the environment because of the different industrial uses, for example, from the mining operations, from ore milling, from chemical industries, dye manufacturing, metal processing, textile mills, petroleum refining. So there can be a number of industries through which the iron basically can come into the environment. And this, when we take very high doses of iron, so it can lead to the fibrosis and the liver enlargement. It can basically also lead to the insulin resistance and diabetes. It can lead to hypothyroidism. It can also lead to cardiomyopathy. So we want that the concentration of iron in the drinking water should not exceed 0.3 milligram per liter, as well as in the effluent discharge the iron should be limited to 3 milligrams per liter. So if we want to remove the iron by using the precipitation method, so we have to add lime at nearly pH 7, so that the ferric which is present, it can be converted to ferric hydroxide. But if we take it to a high pH, in that case, the FeOH whole 4 minus it solubilizes, and again the solubility of this iron may increase, because of which it may be difficult for the removal by the precipitation method. Similarly, if cyanide is present, then the iron can also combine with the cyanide to form complexes. This may interfere with the precipitation of the iron. The two-state hydroxide or sulfate precipitation, it can result in around 0.01 milligram per liter of iron in the effluents. Lead can also go into the environment because of different uses, like for example battery manufacture, the paints and alloys, so they use lead a lot, and lead is quite toxic, so it can lead to adverse impact on the central nervous system and the brain. It can lead to the adverse impact on the reproductive systems, on kidneys, on cardiovascular systems, blood and immune system. So basically it can reduce the IQ levels, it can impair the learning ability, and it can also have a risk of behavioral problems in the individuals if the lead is taken by the individuals. So here in the drinking water, the lead should not exceed 0.01 milligram per liter, as well as in the effluent discharge when we are discharging the treated wastewater to the surface water. So in that case, it should not exceed zero point 0.1 milligram per liter. So for the removal of lead by precipitation methods, we can go for lead carbonate or lead hydroxide. So when we are using sodium carbonate at 9 to 9.5 pH, we can get 0.01 to 0.03 milligram per liter of lead in the effluent. If we are precipitating out the lead with lime at 11.5 pH, then we may get concentration of nearly 0.019 to 0.2 milligram per liter in the effluent. Similarly, precipitation with sulfides at pH 7.5 to 8.5, it may lead to 0.01 milligram per liter of lead in the effluent. So manganese can be used in number of industries. For example, it may come from steel alloys, dry cell batteries, glass and ceramics, paints, varnish, inks and dyes, etc. And manganese can basically impact human health. If we are taking very high concentration of manganese, then it may lead to the problems in the stomach. It may cause laxative effect in the stomach. And for the drinking water, the manganese should not exceed 0.1 milligram per liter, whereas in the effluent discharge, it should not exceed 2 milligrams per liter. So we can remove the manganese by aeration, that is, we can convert this manganese into manganese dioxide, which can be precipitated out from the system. But if we are going for very enhanced aeration, so it may also lead to soluble MnO4 minus ions, which are soluble, and that's why it may interfere with the MnO2 precipitation. So aeration is not also efficient if we are using the pH above 9. So basically we should try to do the aeration below the pH 9. And copper may also enhance the manganese removal through the aeration. So if the copper is present, so then MnO2 precipitation is better in that case. And chlorine dioxide can also be used for the precipitation of manganese. Similarly, ozone and lime can also basically remove manganese from the water or wastewater. Mercury is also a very notorious element which may find its way into the environment from the chlor-alkali industries, cements, electrical electronics, explosive, photography, fluorescent lamps, batteries, pesticides and preservatives and chemicals, petrochemicals, power generation. So everywhere a lot of mercury is used, and this mercury, if it goes into the environment, if it basically comes back to the people, so it may cause a lot of problem, that is it may impair the central nervous system of the humans, and they may lose their control on the body. For example, the case has happened in Japan. It is also known as Minamata disease, where 900 people they died because of the very high mercury pollution, which has basically aggravated, which is biomagnified through the food chain, and it has come into the fishes, which ultimately has come to the humans. And this episode is also known as dancing cats, because the cats were dancing at that time because they also lost control on their body because of very high mercury pollution in the body. So the mercury in the drinking water, it should not be more than 0.001 milligrams per liter, and in the effluent discharge it should not exceed 0.01 milligram per liter. So if we want to go for the removal by precipitation method, so the sulfide precipitation can lead to around 10 to 20 micrograms per liter of mercury in the effluent. Alum co-precipitation may lead to around 1 to 10 microgram per liter of mercury in the effluents. Iron co-precipitation may lead to 0.5 to 5 microgram per liter of the mercury in the effluents. Ion exchange can lead to around 1 to 5 microgram per liter, whereas the carbon adsorption may lead to as low as 0.25 microgram per liter of mercury in the effluents. So nickel may be used in metal processing, steel foundries, motor vehicles, aircrafts, industries, and printing, and as well as the chemical industries. So when we take high amount of nickel, so it may lead to allergy, cardiovascular and kidney diseases, lung fibrosis, lung and nasal cancer. So in the drinking water, the nickel should not exceed 0.02 milligram per liter, whereas in the effluent discharge, it should not exceed 3 milligram per liter. And when we want to remove it by using the precipitation method, so nickel hydroxide has a very poor setting characteristics, and the lime sulfide treatment, and the filtration may lead to the removal of the nickel. For example, it has been shown that the hydroxide treatment at pH 10, so it can result of around 0.12 milligram per liter of the nickel in the effluent. Similarly, that selenium may come into the environment from various industries like paper, fly ash, from the metallic sulfide ores, from the pigment and dyes, where calcium selenide is used. So these industries may induce the selenium into the environment, and if we take very high amount of selenium in our diet, so it may lead to the stomach discomfort, it may lead to headache, rashes, hair loss, fatigue, nausea, vomiting, and weight loss. So these are some of the impacts of the selenium which can be there if we take very extremely high doses, so it can lead to the organ failures as well as death. So selenium should not exceed 0.01 milligram per liter in the drinking water, whereas in the effluent discharge, it should not exceed 0.05 milligram per liter. So when we talk of the selenium removal by precipitation method, so precipitation as sulfide at pH 6.6 may lead to effluent concentration of nearly 0.05 milligram per liter, whereas the iron hydroxide co-precipitation at pH 6.2 may lead to 0.01 to 0.05 milligram per liter in effluent. Alumina adsorption proves to be best, so we can have concentrations as low as 0.005 to 0.02 milligram per liter in the effluent. So silver can come into the environment of number of industries like jewelry, soldering and brazing alloys, batteries, glass coatings, LED chips, medicines, dentistry, nuclear reactors, photography, photovoltaic or solar cells, solar energy, RFID chips, semiconductors. So there can be number of industries from where the silver may come into the environment. So if we are taking high concentration of silver, so it may lead to the discoloration of skin. Silver nitrate or silver oxide may cause breathing problems, as well as it can also cause lung and throat irritation and stomach pain also. So the drinking water standards, the silver should not exceed 0.1 milligram per liter. So if you want to remove the silver by using the chemical precipitation method, so we can go for iron and alum co-precipitation, which may lead to 0.025 milligram per liter of silver in the effluent. The precipitation as hydroxide at pH 11 may lead to nearly 0.02 milligram per liter in the effluents. Activated carbon can also be used for the removal of silver, and we can get concentration of nearly 0.005 to 0.02. And ion exchange may also be used because we want to recover this metal, so the ion exchange can prove to be beneficial in such cases. Similarly, zinc can find its way in through the steel works, rayon fiber manufacture, cooling water systems, plating, metal processing, etc. And high zinc may cause problems like nausea, dizziness, headaches, stomach upset, vomiting, and loss of appetites. And if we are taking the zinc for a long time, so it may basically cause the low levels of HDL, it may cause low immunity, right? And it may also cause low copper levels also. And the zinc should not exceed 5 milligram per liter in the drinking water, whereas in the effluent it should not exceed 5 milligram per liter when we are discharging the effluents to the surface water. And addition of lime and caustic can remove the zinc, and hydroxide precipitation at pH 11 may result in around 0.1 milligram per liter in the effluents. So there can be some limitation of the precipitation methods for the wastewater treatment. For example, when we are treating both industrial waste as well as the domestic waste together, so in that case, the chemical needs to be added to the primary sedimentation tanks, especially if the pre-treatment processes they become ineffective. So in that case, we can go for the chemical addition in the primary sedimentation tank. Similarly, the sludge that is we are getting from the precipitation of the heavy metals, so this may not be stabilized by using anaerobic digestion method because these metals may prove to be toxic to the microbes which are causing the anaerobic digestion. Similarly, the chemical precipitation may also lead to the increase in the total dissolved solids of the wastewater that is being treated. So these are some of the limitations of the precipitation methods if we are going for precipitation in the wastewater treatment. So now let us discuss a few problems based on the solubility product that we have already discussed. So the problem 1 states that the KSP values for the calcium sulfate in the water at 25 degrees centigrade is 1.96 10 to the power minus 4. So we have to determine that what is the equilibrium calcium concentration in the saturated calcium sulfate solution if we assume that ideal behavior is there. So we can write down the equation. For example, this equation tells us how the calcium sulfate is getting dissociated into calcium and sulfate. So we can write down the solubility product constant here, which is equal to the molar concentration of calcium and molar concentration of the sulfate. So this is equal to 1.96 into 10 to the power minus 4. So then we can basically we write down that the molar solubility, because 1 molar of calcium sulfate is giving rise to 1 molar of calcium as well as 1 molar of sulfate. So these two are having the same molar concentrations at equilibrium. So we can write down this as M, and so this becomes M square. So this means that the calcium is having a molar concentration of nearly 1.4 into 10 to the power minus 2 at equilibrium, and we can convert this into milligrams per liter by multiplying it by the molecular weight of calcium. This gives us the concentration of the calcium as 561 milligram per liter in the water. Question 2, we have to compute the solubility of the cadmium hydroxide in water at 25 degrees centigrade, and we have to assume that the solubility product is 5.9 into 10 to the power minus 50. So we can see that the reaction for cadmium hydroxide getting dissociated into cadmium and 2 moles of hydroxide. So cadmium hydroxide is giving 1 mole of cadmium and 2 moles of hydroxides. So we can write down the expression for the solubility product like this. That is, this is cadmium, concentration of cadmium into the concentration of OH minus whole square. And because the molar concentration of the hydroxide is twice that of the cadmium concentration, so we can just replace it here with the equilibrium molar concentration of cadmium, and the hydroxide molar concentration, which is 2 times the cadmium concentration whole square. So this gives us the solubility product. So this means that we can calculate the value of the cadmium concentration at equilibrium. So this comes out to be 1.14 into 10 to the power minus 5 moles per liter. As we know that 1 mole of cadmium hydroxide is giving rise to 1 mole of cadmium ions. So the molar concentration of the cadmium and molar concentration of cadmium hydroxide will be same. So this means that the solubility of the cadmium hydroxide at this point will be equal to the molar concentration of the cadmium, right, into multiplied by the molecular weight of the cadmium hydroxide. So this gives us the solubility of cadmium hydroxide to be 1.67 milligrams per liter. Then we are having a problem on barium sulfates, and barium sulfate is used for medical imaging of gastrointestinal tract, and here it is having a solubility product of 1.08 into 10 to the power minus 10 at 25 degrees centigrade. So we want to find out that if whether the barium sulfate will precipitate if we are adding 10 ml of 0.002 molar of sodium sulfate solution into the 100 ml of 3.2 into 10 to the power minus 4 molars of barium chloride solution. So we know that the barium sulfate here can be dissociated into barium and sulfate ions. So we can say that the solubility product of the barium and sulfate will be 1.08 into 10 to the power minus 10. So if we find out the ion product of barium and sulfate, so this we have to calculate so that we can calculate that whether the barium sulfate will precipitate or not. Because here we are considering that the sodium chloride is having a very high solubility in water. So we will find out that whether the barium and sulfate, they are having the ionic product which is greater than KSP value, so it will precipitate, otherwise it will remain in the solution. And here we are adding 2 solutions, one is 100 ml and other is 10 ml. So then we have to calculate the concentrations or the molar concentrations at for 110 milliliters of water of the solution. So we can calculate the moles of the barium which is present in the original solution, right? So we can have the concentration present here, that is the molar concentration is 3.2 into 10 to the power minus 4 moles per liter. So in 100 ml it will be nearly 3.2 into 10 to the power minus 5 moles of barium will be present. So in 110 ml of the solution, we are having nearly 2.9 into 10 to the power minus 4 moles of barium. Similarly, we can also calculate the moles of sulfate present in the sodium sulfate solution. So it is nearly 0.0020 moles per liter, and this is nearly 2 into 10 to the power minus 5 moles of sulfate present in the solution for 10 ml of solution. Similarly, we can also calculate the molar concentration of sulfate which is present in 110 ml of the solution. So now we get these two values, that is the 2.9 10 to the power minus 4 moles of barium and 1.8 10 to the power minus 4 moles of sulfate. So if we multiply it, so that we can get the ionic product here. So this ionic product comes out to be 5.2 10 to the power minus 8. Now this ionic product is greater than the Ksp value. So in this case, we predict that the barium sulfate will precipitate out, right? So barium sulfate will precipitate out because when the two solutions are mixed, because the ionic product of the two ions, that is barium and sulfate, so it is higher than the solubility product. So it will continue to precipitate till the Ksp values or till the equilibrium condition comes and the Ksp value is nearly 1.08 into 10 to the power minus 10. So with this we stop here, and these are the references that we have used for this lecture. Thank you.